When we're looking at resonant circuits, we often use a term called the quality factor, or Q of the circuit, and this is a measure of how much energy is stored in the circuit to how much energy is lost. On a per cycle basis. So we can use a pendulum analogy for RLC circuits. So here's our pendulum, and we know that it can swing to either side. When the pendulum is at the height of its swing, it contains all potential energy. And when it's at the bottom of its swing, it has all kinetic energy. For a lossless pendulum, the kinetic energy and the potential energy, the sum of those is a constant. We know that real pendulums have loss. There's friction in the string, friction in the connection to where the string ties to the swing point, etc. And so there would actually also be a lossy term. When we look at our circuit, we know that our circuit has loss, and that loss is modeled as a resistor. So for a circuit, Q is defined as energy stored times omega naught divided by the average power dissipation. And as we said before, for an RLC circuit, energy sloshes between the inductor and the capacitor every cycle, with some of it being lost in the resistance. Alright, so let's examine our parallel RLC circuit and see if we can figure out what the Q is equal to. Alright, here we have our input current source, and it's a sinusoidal current source. So if we looked at this versus time, we would see our input current source oscillating with an amplitude that we'll call I peak, IPK. So at resonance, IN reaches I peak, and the voltage across the capacitor will be maximal. So we can say VC is equal to I peak times R. All the energy stored in the capacitor, the energy in the capacitor is maximum, and there's none in the inductor. So we can say that our peak energy stored E peak is equal to 1/2 times the value of the capacitance times the voltage of the capacitor squared, which is equal to 1/2 C times I peak times R squared. We also have some current flowing into the resistor. So the average power dissipated by the resistor is 1/2, we'll call this PR, is 1/2 times the I peak value squared times R. This is just the RMS power dissipated by a resistor. We can define the quality factor as the ratio of the energy stored to the average power dissipation. In other words, we can say Q is equal to E peak times omega divided by the average power in the resistor, PR. This is equal to omega naught times 1/2 C times I peak times R quantity squared divided by 1/2 I peak squared times R. Substituting our value for the resonant frequency, 1/square root of omega LC, we can reduce this Q value to R times C divided by the square root of LC. Or we can also rewrite this, if we choose, as R divided by the square root of L divided by C, just by moving C into the denominator. This is an interesting term because this is what we look at normally as a characteristic impedance if we were looking at a transmission line, for instance. In the limit, our parallel resistance goes to infinity. In other words, it would be an open circuit. And so in the limit, of Q as R goes to infinity, Q would go to infinity. There would be no loss in the circuit, and the circuit would oscillate forever. Alright, so we can write a couple of things out. At resonance, the impedance of our capacitor is equal to 1/omega naught times C, which is equal to square root of LC over C, which is equal to square root of L over C. The inductor has an impedance of omega naught times L, which is equal to L divided by square root of LC, which is equal to square root of L over C. Again, we see our characteristic impedance for these components. So we can write our Q in terms of either the resistive and capacitive component or in terms of the resistive and inductive component. So we know Q is equal to R divided by square root of L over C, which means that Q is equal to R divided by ZC, or omega naught times R times C. Or we could also say that Q is equal to R divided by ZL, which is equal to R over omega naught times L. Alright, so now we have a metric of the quality factor of our RLC tank, which is basically saying how large is our resistance relative to the rest of the circuit. And in order to have a very large Q, we see that we would like to have a small inductance or a large capacitance, and we'd also, of course, like to have a very large resistance. Now we'll look at branch currents in the circuit in the next part of the lecture.